Hey everyone, Mr. Hauk here. In today's video, I'm going to talk about the solutions to the quiz review for Unit 2 vectors. Let's go ahead and get started. In number 1, we want to write the vector AB in component form, given the points A equals 4, negative 7, and B equals negative 3, negative 2. Notice the component form means that we need to have our horizontal component first and our vertical component second. And to put a vector in component form, we take the terminal point, in this case B, we subtract the coordinates of the terminal point minus the coordinates of the initial point. So vector AB is going to be x2 minus x1, comma y2 minus y1. Horizontal component will be negative 3 minus 4, and the vertical component will be negative 2 minus negative 7. Be careful with your double negative, make sure that you turn it into an addition. When you subtract these, you get components negative 7, positive 5. In problem number 2, we want to write the vector AB in component form given the graph. So similar to number 1, but instead of given the points, instead of being given the initial and terminal points, we're given the graph of the vector. Well, notice that we still have the initial point A, and we still have the terminal point B, and I know A is initial and B is terminal because B has the arrow. So you have a couple options. You can write the coordinates of A and B and solve the problem algebraically like we did in number 1, or you can simply count the horizontal and vertical components. Notice that horizontally, to go from A to B, I would have to go to the right 4 spaces, so that would be a positive 4 for a horizontal component, and then I would need to go down 7 spaces. So we'd have a negative 7 for the vertical component since down is a negative direction on the y-axis. In problem number 3, we want to write vector PQ as a linear combination of the standard unit vectors I, j, and k. Given that point P is negative 2, 8, 5, and point Q is negative 4, negative 9, negative 6. So this problem, again, is very similar to number 1. One of the differences is we're going to have a vector in 3-dimensional space. But let's go ahead and find vector PQ. So again, we're going to take the terminal point, subtract the initial point. So we're going to do x2 minus x1, so negative 4 minus negative 2, y2 minus y1, so negative 9 minus 8, and then z2 minus z1, negative 6 minus 5. Performing those calculations, we get negative 2, negative 17, negative 11. Now notice that this is in component form. I want to turn it into a linear combination of the standard unit vectors I, j, and k. So negative 2 is negative 2i, negative 17 minus 17j, negative 11 minus 11k. In problem number 4, we want to find the magnitude of vector CD given the initial point C and the terminal point D. Well, to find the magnitude of a vector, first we have to have the vector written in component form. To find the vector CD in component form, again, we're going to do the initial point minus the terminal point. So we're going to have x2 minus x1 to get 6 minus negative 9, y2 minus y1 to get negative 3 minus 2. Performing those calculations, we get the vector in component form, 15, negative 5. Once your vector is in component form, then you can take the square root of the components squared and add it together. Here's 15 squared, here's negative 5 squared. When performing this calculation, make sure that you're careful with the negative 5 squared. It's negative 5 times negative 5, so you'll be getting a positive 25. Once you add these pieces together, you get the square root of 250. We know that 250 is 25 times 10, and 25 is a perfect square, so this simplifies to 5 square root of 10. In problem number 5, we want to find the magnitude of the vector v, which is negative 3i plus 5j minus 6k. Now, very similarly, we can go ahead and write this vector in component form. So instead of having negative 3i plus 5j minus 6k, I wrote it as its components, negative 3, 5, negative 6. Then to find the magnitude of vector v, we take each of these components, square them, add them together, take their square root. So you can see we have negative 3 squared plus 5 squared plus negative 6 squared. Once again, be careful with your negatives. Negative 3 squared is positive 9, 5 squared is 25, negative 6 squared is positive 36. Adding them all together, you get 70, which cannot be simplified since there are no perfect squares that make up 70. So the answer here is simply the square root of 70. In number 6, we want to find the magnitude and direction of the vector graph to the right. One of the first things to notice, and actually one of the first things that I'm sure threw a lot of students off when they tried the review, is that the x-axis and the y-axis are scaled by 2's. Notice 2, 4, 6, 8, 10. Same for the x-axis, 2, 4, 6, 8, 10. So the first thing that I want to do is I want to write this vector in component form. That way I can find the magnitude and direction fairly easily. So noticing that we have initial point right here, we have the vertical or the terminal point here where the arrow is. That means that horizontally I would have to go to the right 5 spaces, but since the spaces are going by 2's, I'm going to the right 10. Right is a positive direction, so my horizontal is a positive 10. Then I would need to go down 2 spaces, but again, this is scaled by 2's, so I'm really going down 4. This makes my vertical component a negative 4 since down is a negative direction. Once we have our vector written in component form, let's go ahead and find the magnitude and direction. So the magnitude is going to be the square root, 10 squared plus negative 4 squared. That would be 100 plus 16, you get 116. And when you do your calculation, 116 is 4 times 29. We know that 4 is a perfect square, so we get 2 square root of 29. For the direction, we know it's the vertical component divided by the horizontal component, so we get negative 4 divided by 10. Simplifying, that gives us a direction of negative 2 over 5. In problem 7, we want to find the direction of vector PQ if the initial point P is 8, 4 and the terminal point Q is negative 2, 8. First, just like in the previous problem, let's go ahead and write our vector in component form. So we will do terminal point right here minus initial point right here. We get x2 minus x1, negative 2 minus 8, y2 minus y1, 8 minus 4. This gives us components negative 10 and positive 4. Once again, to find the direction of a vector is the vertical component, the second component, divided by the horizontal component, the first component. We get 4 divided by negative 10, which again reduces to negative 2 over 5. In problem 8, we want to find the unit vector in the direction of vector tx, given initial point t is negative 9, negative 10, and terminal point q is negative 7, negative 2. Well, in order to find a unit vector in the direction of a certain vector, we have to take that vector and divide it by its own magnitude. So we need to start by finding the vector tx. I'm going to go ahead and find vector tx using its initial and terminal points. So I'm going to take x2 minus x1, which is negative 7 minus negative 9. That gives me the first component of 2. And then y2 minus y1, which is negative 2 minus negative 10, to give me the vertical component of positive 8. So this is vector tx, written in component form. Now we need to find the magnitude of vector tx. Well, to do that, we take the square root, square the magnitudes, square the components, add them together. So we get square root 2 squared plus 8 squared. That gives you square root of 68. And we know the square root of 68 is 4 times 17. 4 is a perfect square, so this simplifies to 2 square root of 17. Now that we have vector tx and vector tx's magnitude, to find the unit vector in the direction of tx, we take that vector tx, which was 2, 8, divide it by its own magnitude, which was 2 square root of 17. So we get 2 divided by 2 square root of 17, 8 divided by 2 square root of 17. Let's start doing some simplifying. So 2 and 2, they reduce with each other. We just get 1 over square root of 17. 8 and 2, they reduce with each other. We get 4 over square root of 17. But we all know that we don't like square roots in denominators, so we're going to multiply the square root of 17 on top and bottom for both these pieces. This ends up giving us square root of 17 over 17, 4 square root of 17 over 17. In problem number 9, given vectors u and v in component form, we need to find negative 4u plus 7v. Well, luckily, u and v are already written in their vector component form. So all we need to do is distribute negative 4 to vector u, which I've done right here, and 7 to vector v, which I've done right here. So negative 4 times 12, we get negative 48. Negative 4 times 7, we get negative 28. Over here, 7 times negative 10, we get negative 70. And 7 times negative 9, we get negative 63. Now, we need to add these vectors together. So we're going to add their components together. The horizontal components for each vector are here in green. Negative 48 plus negative 70 gives us negative 118. The vertical components are here in blue. Negative 28 plus negative 63 gives us negative 91. And this is the sum, negative 4 times vector u plus 7 times vector v. In problem number 10, given all 4 of these points, we want to find 3 times vector ab plus 9 times vector cd. Excuse me, guys. So, vector ab, we need to go ahead and write in component form. Again, we're going to do terminal point minus initial point. This is negative 9 minus negative 3 to get negative 6. 3 minus 7 to get negative 4. So negative 6, negative 4 is vector AB in component form. Similarly for vector CD, terminal point D minus initial point C. 0 minus 9 to get component negative 12. Negative 7 minus 5 to get component negative 12 here. And I should have said negative 9 earlier. So now that we have these two vectors in component form, we can multiply them by these scalars. We're going to multiply vector AB times scalar C, vector CD times scalar 9. That's done right here. So notice that 3 times vector AB, I get vector with components negative 18, negative 12. 9 times vector CD, I get vector with components negative 81, negative 108. Now we're at the point where we can add them. So we just add their components. The horizontal components are here in green. If I add them together, I get negative 99. And our vertical components are here in blue. If I add those together, I get negative 120. In problem number 11, we want to find the resultant vector of vector AB plus vector CD minus 3 times vector EF. Notice vectors AB, CD, and EF have been graphed over here on the right. My strategy was to write each vector in component form and then perform the operations algebraically. Notice that for vector AB rather, A is the initial point, B is the terminal point. So we're going to write them in their component form, horizontal, then vertical. So for vector AB, notice horizontally, we had to go to the left twice, which is a negative 2 for that component since left is a negative direction. Vertically, we had to go down 3, so we have negative 3 as our vertical component. For vector CD, C is initial, D is terminal. Horizontally, we had to go to the right 3, so a positive 3 for our horizontal component. Vertically, we had to go down 2, so we have minus 2 for our vertical component. And then finally, for vector EF, E is initial, F is terminal. Horizontally, we had to go to the right 1, so positive 1 for our horizontal component. Vertically, we had to go up 6, positive 6 for our vertical component. With all 3 of those vectors written in component form right here, now we can perform the operations. We want to do vector AB plus vector CD minus 3 times vector EF. I'm going to go ahead and distribute the negative 3 to vector EF, giving me negative 3, negative 18 for the components. Then all I need to do is combine all the components. Horizontal components are highlighted in green. They give me a total sum of negative 2. Vertical components are highlighted in blue. They give me a total sum of negative 23. In problem 12, given vectors u and v in component form, we want to find the vector graph below that could be vector u minus 2 times vector v. Well, let's go ahead and perform the algebra here. Vector u minus 2 times vector v, right over here, we know that we're going to need to distribute the negative 2 to vector v. This gives us negative 4 and positive 2. Then, combining these vectors after we've distributed the negative 2, horizontal components 1 and negative 4 combine to be component negative 3. Vertical components 3 and 2 will give us a 5. Then what we need to do is we need to find which of the vectors graphed has the correct components, negative 3, 5. Well, notice that vector A, because of the way it's set up with the terminal point up here, it's going to be going to the right 5, which is a positive 5 for the horizontal, up 3, which is positive 3 for the vertical. That does not match what we needed to match, so A is wrong. If we look at vector B, which we can already see is correct, notice that because the terminal point is up here to the left, we would have to go from initial to terminal, left 3, so that's a horizontal component of negative 3, and then up 5, which is a vertical component, a positive 5. For C and D, you can also see the components there if you want to pause the video and take a look at them, but know that answer choice B has the correct components of the graph vector. In problem number 3, a commercial airplane is traveling south going 515 miles per hour. So I went ahead and drew my vector right there, going 515 miles per hour in the south direction. Suddenly, a strong crosswind traveling west to east hits the airplane at 230 miles per hour. So west to east, starting in the west, traveling to the east, we have the crosswind going 230 miles per hour. And we want to find the magnitude and direction of the resultant vector. Well, the resultant vector is from the beginning of the first vector to the end of the second vector. So there's our resultant. In component form, the horizontal component is a positive 230 because moving in the east direction is a positive direction. For the vertical component, it is a negative 515. Be sure that you take note of that negative because the airplane is moving south, which is a negative direction. So to find the magnitude, we know we're going to take the square root, take the components, square them, add them together, take their square root. Performing those operations in the calculator, you get that the magnitude of the resultant vector is roughly 564.03 miles per hour. That allows us to cancel out C and D here. The direction, however, we know the direction is the vertical component divided by the horizontal component. So our direction is negative 515 divided by 230, which will reduce to negative 103 divided by 46. In problem number 14, we have a 115-pound box on a ramp that makes an angle of 32 degrees. So I'm going to go ahead and set up my picture here. We have our inclined plane. We have the 90-degree angle. We have the angle of incline, 32 degrees. And we know that the weight of the object is 115 pounds. Now, we have a rope tied to the box from a post at the top, and it's keeping to keep the box in position. So here's our post. This is our rope tied to this box. And essentially what we want to know is how much force is being exerted on the rope by the box. So what we're looking for is the parallel force. This is the force right here that we're looking for. Well, we know that the weight, mg, is 115 pounds. We know the angle of incline between the inclined plane and the horizontal is 32 degrees. So our equation is that the parallel force is mg, the weight, times the sine of theta. Again, plugging in our weight and our angle, we get 115 times the sine of 32 degrees, which gives us 60.94 pounds. So the force being exerted on the rope by the box is 60.94 pounds. In our last problem on the review, we want to select all of the vectors that are unit vectors. Remember that to be a unit vector, the magnitude of the vector has to equal 1 exactly. So let's look at all of these different vectors and see which ones have magnitudes of 1. Looking at vector A, which has components 7/25 and negative 24/25, when we square the components, we get 49 over 625 plus 576 over 625. This adds up to 625 over 625, which is 1, and we know the square root of 1 is 1. So A is a unit vector. B, however, we can see is not a unit vector. When we take 4/5 squared, we get 16 over 25. When we take 2/5 squared, we get 4 over 25. 16 25ths plus 4 25ths is 20 25ths. And you take the square root of 20 25ths, you will not get 1. Answer choice C. Components 2 root 5 over 5 and negative 2 root 5 over 5. If we go through and square them, we can see the math right here. 2 root 5 over 5 times 2 root 5 over 5 gives us 4 times 5, which is 20 over 25. The second piece also gives us 20 over 25. Adding these together, we get 40 over 25, which we know when we take the square root will not equal 1. So C is not a unit vector. Then lastly, we have vector D from answer choice D. We have vector 5/13, 12/13. 5/13 squared is 25 over 169. 12/13 squared is 144 over 169. And adding those pieces together, we get 169 over 169, which is 1, and we know that the square root of 1 is 1.